Heat of formation is really exactly what it sounds like. Heat that is produced, or the change of heat, when a compound is formed from its elements. So for example, if we have this calcium plus 2 carbon, we get calcium carbide. The heat of formation for that is minus 59.8 kilojoule per mole, and we can see it's a minus sign, so that means it's exothermic. When it was combined, when the calcium and the carbon combined, it produced 59.8 kilojoules of mole that was released. It exited the system. Now, conversely, when we break that compound down, when the CaCa2 is broken down to the calcium and carbon, it shows that it's an endothermic process. We needed heat in order to break it down. So heat went into the system to break it down. So we show a enthalpy diagram here. We want to know, is this reaction endothermic or exothermic? Well, we can see it's a negative sign. So in order to create water, H2 plus 1/2 O2, it is an exothermic reaction. It produced heat, it produced energy, as we can see. So we're looking at heats of reaction here. How can we find how much heat was produced in a reaction? Well, we can find the enthalpy change in a couple ways, either by calorimetry through experimentation, or by using the enthalpies of formation, and then we can calculate the theoretical enthalpy. And in order to do that, we need to know standard heats of formations, and we find that in a table. Here are some standard heats of formation, delta HF. Here's another table. Heats of formation here. You can find many heats of formation in many different tables. Let's find heats of reaction using the heats of formation, which we get from tables. Chemical reaction can be thought of a two-step process. The reactants are broken down into elemental states, and then those elemental states are formed into products. Now, this is not really how it happens, but we can use this to represent energy change. We will get to that. It will make more sense as we get to the problem. So let's look at this equation here. So for a reaction that occurs at standard conditions, you can calculate the heat of reaction by using the heats of formation. Now, these two equations are the exact same thing. It's just sometimes you will see it written like this and other times like this, but they're the same thing. Basically, they're saying the heats of reaction is equal to the sum of the products of the heats of formation minus the sum of the reactants, the heats of formation. And again, this one says the same thing. So basically, we can sum up the heats of formation of the products, and then we can sum up the heats of formation of the reactants, and then subtract that. Let's look at this. Find the enthalpy of reaction for the following reaction. So given this equation, we're going to find delta H, heat of reaction, or enthalpy of reaction. That again, remember, equals the sum, the heat of formation for the products, minus the sum of the heat of formation for the reactant. Now, these are actually easy to find. All we look at for the heat of formation, we just look at a table. So let's look at some of the heat of formation for the products. So the product, CO2 and H2O. We have 2 CO2 plus 4 H2O. What is the heat of formation for carbon dioxide? Heat of formation for carbon dioxide is minus 394 kilojoules per mole. Then we are going to look at the heat of formation. We're going to sum that up with the heat of formation with water. Heat of formation for water is minus 286 kilojoules per mole. We're going to subtract that from the reactants, or the reactants from that. So the reactants are 2CH3OH plus 3O2. And CH3OH, heat of formation, is minus 239 kilojoule per mole. Oxygen is actually 0. Now the thing is, we can't just go ahead and add these up. We need to look at the balanced equation. The balanced equation shows that there are different mole quantities. So that means we're going to have to multiply those coefficients by those heats of formation. So for carbon dioxide here, we're going to have to multiply this one by 2. For water, we'll multiply that one by 4. For methanol, we'll multiply it by 2. And that comes out to be, okay, so we add this up. This becomes minus 1932 kilojoules per mole minus, or really a plus, 478 kilojoules per mole, which equals a negative 1454 exothermic. Let's look at another one. 2CaC2 plus 5O2 goes to 2CaO plus CO2. And again, I apologize, this should be calcium plus 5 oxygen. Calcium oxide. So let's sum up the heats of formation. What is the heat of formation for calcium chloride? All right, so heats of reaction is equal to the sum of the heats of formation for the products minus the sum of the heats of formation for the reactants. So let's write the heats of formation for the products. That is 2CaO plus 4CO2 subtract 2CaC2 plus 5O2. Okay, so we have the sums of the product minus the sum of the reactants. What is this heat of formation for calcium oxide? Heat of formation for calcium oxide is minus 635.1. Now we're going to have to multiply that by 2. And the heat of formation for carbon dioxide is minus 393.5. And again, we're going to have to multiply that by 4. We subtract 2 times the heat of formation for calcium carbide, which is minus 59.8. Oxygen does not have the heat of formation. Since oxygen is diatomic, diatomic molecules do not have heats of formation, as do elements, single elements. So if it's a single element or diatomic, you will not have a heat of formation. It will be 0. Let's add these up, and we get minus 1270.2 plus negative 1574 minus a negative 119.6. Come out with a heat of reaction that equals a negative 2724.6 kilojoules, and that's very exothermic.